Okay, so for this lesson, we're going to talk about exponential growth and decay. Now, I believe on the first day of differential equations, I might have gone over this example with you, but I'm just going to recap it just to make sure everybody's on the same page. Okay, so if you see this wording, the rate of change, obviously rate of change is talking about derivative of some quantity y, that could be anything. A lot of times I would say it's probably a population or something like that, is directly proportional. That means you're being multiplied by some constant of proportionality k to the y actually itself, okay? If you set up a differential equation based on that wording, let me just switch to this color, what you're going to end up getting is the rate of change, dy dx, okay, of some quantity, okay, is directly proportional to y, is equal to k times y. Okay, remember that k is a constant, so you're not going to view k as a variable. You're going to think of it like as if it's a 2 or a 5 or a 7. All right, so we separate our variables. I'm going to cross multiply, so I'll end up with dy equals ky dx. I'm going to divide both sides by y to get all the y's on one side and leave k on the right because, again, I'm assuming that that's like a 2 or a 3 or something like that. So on the left-hand side, I have 1 over y dy. And on the right-hand side, I have k dx. So now I'm going to go to the part where I integrate both sides. Integral of 1 over y comes out to be ln of absolute value of y, although the absolute value really won't matter a lot in this case, is equal to kx, okay? Because obviously, again, if you integrate 2, you get 2x. If you integrate 3, you get 3x. If you integrate k as a constant, you get kx. Obviously, again, don't forget plus c. We're going to finish up solving for y by raising both sides to be the exponent of e. So when I do e to the ln, those cancel out to just come out to be y. On the right-hand side, think of that as e to the kx times e to the c. E to the c is just a constant to a constant, so you could just think of it as c by itself. So we eventually end up with y equals c e to the kx, or with the way you might remember it from when you were in algebra is that a equals p e to the rt. Okay, so basically you're going to end up with an exponential expression. So I want you to keep in mind, when you see something like this, the rate of change is directly proportional to something, know that that's always going to come out to be some sort of an exponential relationship. It may not always be p to the rt. There might be an extra number added or subtracted onto that, but at least it can kind of have like, a similar shape and things like that. Okay, so let's take a look at this first example. Let P of t represent the number of wolves in a population when t is greater than 0, obviously, because it's time. The population P is increasing at a rate directly proportional to 800 minus P. Okay, so to make a differential equation for that, we're talking about the rate of change of population over time. So dp dt is directly proportional, that's where k comes in, to 800 minus P. So this one's still going to end up being an exponential model, but it's going to come out to be a little bit different because of that 800 minus p and not just p itself. So again, I'm going to cross multiply and get, my values separated. So as I multiply both sides by dt, I get k times 800 minus p dt. And I divide both sides by 800 minus p to get all of my p values on the left-hand side. So I'll have 1 over 800 minus p dp equals k dt. So now when you integrate on the left-hand side, this is where you need to be careful. This is an example of one that you would end up doing a U-substitution for, where your u, let me just change colors for a second, your u would have come out to be something like 800 minus p. So as you integrate that, take the derivative of that, you would have gotten negative 1 dp, something like that. So if you notice that you're actually missing the negative 1 that you would need to complete your du, so you need to put that negative back out on the outside. You don't actually have to show the whole U-substitution. You just have to know that that was definitely part of the process to make sure that when you integrate, you get the right integral. So similar to the previous problem, I end up with 1 over something with no parentheses to a power. So that's how it's going to come out to be an ln. So I get negative ln absolute value 800 minus p. On the right-hand side, again, k is a constant, so I get kt plus c. Now, before I can raise both sides to be exponents of e, I need the ln to be by itself. So I'm going to divide everything by negative 1. Okay, so let's think about what happens here. On the left, I have 800 minus p. On the right, k is just a constant. So if I divide k by -1, isn't that still just a constant? This I can literally leave as just kt if I want. If you want to make it negative kt, that's fine. But again, remember how like that idea of a constant times a constant or a constant divided by a constant stays constant. Same idea when you do the -1 into the c. Okay, that constant when you divide it by -1, still going to be some constant number. So that's how I get something like this. So you can see in this example, it probably wasn't the end of the world if you had forgotten that negative for your du, but in other problems it will matter. So I want you to make sure you remember that. Okay, so similar to the previous question, when you have ln by itself now, you're going to raise both sides to be exponents of e. As you do that on the left side, you'll have 800 minus p. On the right-hand side, this will become ce to the kt, and then you just have to finish solving to get p by itself. So I'm going to get 800 on the right-hand side, and then I'm going to divide everything by -1. As I do that again, -1 will be absorbed into this c because of the fact that it's just a constant. So I end up getting, I don't know why it's zooming in like that, that this comes out to be just c e to the kt. And when I divide -800 by -1, I get plus 800. Okay, so this is what I would probably say is a start to my general solution. Most likely you're probably going to want to try to solve for k and have it only as c if that was a general solution. But this is enough to solve the first part of this situation. Okay. So we're now going to take the information provided and we're going to use it to solve for the additional parts of this problem. All right, so let me just erase some of this guy on the left. Okay, obviously you can always rewind the video if you need to go back and move this guy over. And now let's solve for the remaining parts of this. Okay, so here's my initial model for this situation. The initial population is 500 wolves. That means there are 500 wolves when t equals 0. So use the fact that when t equals 0, p is equal to 500, and use that to solve for c. So I'll end up with 500 equals c e to the k times 0, obviously coming out to be 0. And then e to the 0 power is just 1. So 500 equals c times 1, basically, plus 800, or c equals -300. Okay, so I have p equals -300. E to the kt plus 800. You'll need another point to be able to actually solve for k. So if you look at part C of this, it says when t is 2, there are 700 wolves in the population. So similar to what we just did to solve for c, we'll plug in the information provided and use that, go work backwards to get what that k value comes out to be. Okay, so I have 700 equals -300 e to the kt, I'm sorry, k2, okay, times plus 800. So what I'm going to do here is I'm going to minus 800 from both sides, so I end up getting -100 on the left, -300 on the right, e to the 2k. You will notice the fact that you're solving for k in this situation, you're going to have to use logarithms at some point. You'll have to get rid of this -300 in the front, though, before you can log both sides and have that log actually cancel with the e. I would probably say leave things as exact values until your final answer, okay? And obviously, don't forget the AP standard of rounding to 3 decimal places. At this point, I can now ln both sides. That allows me to bring that 2k down in front. So I have ln of 1/3 equals 2k. And if you recall, ln of e is actually equal to just 1. So pretty much I can just leave that ln of e off. That just multiplied by to become a 1. And then I can finish by dividing both sides by 2. So if I needed to write this down for the AP exam, this is fine actually. ln of 1/3 divided by 2. Okay, so I can actually leave this as k equals ln 1/3 over 2, or if you want to actually make it a decimal, it will be k equals -0.549. Okay, so our exponential model for this exact situation is p equals -300 e to the -0.549 t plus 800. I want to go back to something I mentioned on that first day. Most of what we're doing in these problems is just algebra. The only part of this that was actually calculus was the stuff that we did in the very beginning to get p equals ce to the kt plus 800 based on the fact that we had this differential equation saying that we were directly proportional to 800 minus p. Okay, so if you need to go back and brush on some of your algebra for this, that might be a good idea. So once you have this model, obviously if I need to find out what's the population at a specific time, I can plug in that t, or what time is there a specific population, I can plug in that p. Here's where I would probably bring back a little bit of calculus into this question. Find the limit as t goes to infinity of p of t and explain what it means in the context of this problem. Okay, so we're doing the limit as t goes to infinity of this whole expression up here, negative 300 e to the negative 0.549t plus 800. Okay, so now if you remember, when you're working with limits, if you are adding or subtracting, you can take the derivative of each part individually. So I'm going to take the limit of each part individually. So I'm going to take the limit as t goes to infinity of that negative 300 e to the negative 0.549t. Forget the negative 300 for just a second. Focus on the fact that that is an exponential with a negative exponent. If you graph an exponential with a negative exponent, whether or not it's below the x-axis or above the x-axis, technically below in this case, you will see that it eventually heads to 0. Okay, so I'm going to end up having 0 for the limit of that whole e expression. As t goes to infinity, 800 doesn't have a t in it, so it would stay 800. So the limit as t goes to infinity of p of t would be 800. And what that means in this case is that the population is capped at 800. Okay, so if you think of this in terms of real life, for example, wolves or whatever, wherever they're living, there's only a finite amount of space that they can actually live in. So eventually the population is going to have to get capped out. 800 is going to be the maximum population. So maybe actually that's what I'll go back and do. Instead of saying it's capped at 800, this is the maximum population. The max population is 800. Okay, oopsies. All right, well, sorry, jumped ahead. Okay, so I want to do one more example, and then that way you guys can be able to do your homework problem for tonight. Okay, so I'm going to skip ahead. Number 2 is also another algebra question, so I'm just going to skip ahead, but if you want to see the answer to that, feel free to go to our solutions in Google Drive. I'd like to do a question like number 3. Okay, so you should know that question number 3 was an actual AP question, so you should be prepared for, possibly something like this when you take your AP exam. So thankfully in this question, you don't have to create the differential equation. It's already provided to you. It actually also already gives you that k value. So I know it's kind of weird, but if you think of it as like dw dt is equal to k times w minus 300, similar to that last question, it's basically saying it's directly proportional to w minus 300. But again, they already gave you the k value, so that makes things a little bit easier. So if they give you the differential equation, this one is going to be more about application. So you're going to see a lot more calculus in this question. Okay, so first question, and there's going to be some interesting parts to it. Use the line tangent to the graph of w at t equals 0 to approximate the amount of solid waste in the landfill contains at the end of the first 3 months of 2010. So in terms of time, that means t equals 0.25. So when you want to make a line tangent, obviously remember linear approximation. So you're going to have L of x equals f of a plus f prime of a times x minus a. Okay, in this particular case, you're talking about tangent to the graph of w at 0. So maybe I'll call it L of t because it's something about time, is equal to w of 0 plus w prime of 0 times t minus 0. So you're going to have to be careful, especially with this w prime of 0. This function is not a function of t, okay, this dw dt. It is technically, but in like a weird way. It's more a function of w. So you need to actually plug in the initial w value into this equation to get w prime of 0. Okay, so they give us that w of 0 is 1400. Okay, to get w prime of 0, so I'll put this in like quotations because it's a little weird, you're going to plug into dw dt at the point where you have the point 0, 1400. Okay, so this is your t and this is your w. So when you plug in, it's 1 over 25 times 1400 minus 300. And if you simplify this, this eventually comes out to be 44. So 44, and then obviously t minus 0 is just t. Okay, that would be your equation of the line tangent. So you can see you're still using your general model for the line tangent, but it's a little tricky when you get to the point of finding the derivative value. Okay, so we're using this to approximate the value of 0.25, like the amount of waste at 0.25. Okay, so you're going to end up plugging in 1400 plus 44 times 0.25. So eventually when you simplify that, that comes out to be 1411. Okay, so you would say there's approximately 1411, I believe it's in tons, obviously watch your units, yep, tons of waste at 0.25. Okay, part B, find the second derivative in terms of W and use it to determine whether your answer to part A is an underestimate or an overestimate at t equals 0.25. So again, here's something where you're going to have to be careful calculus-wise. dw dt was equal to 1 over 25 times w minus 300. Okay? If I'm taking the derivative with respect to t, it means I have to follow up every variable that I take the derivative of with d of that variable over dt. That's implicit differentiation that I'm bringing back here. So when I take my second derivative, d squared w over dt squared, okay, 1 over 25 is just a constant that stays out front. The derivative of w becomes 1, but I have to follow that up with dw dt because of the fact that I'm taking it, like using implicit differentiation, it's not all in terms of t. Negative 300 would come out to be 0. And to fully get in terms of w, I have to actually plug back in, and if you remember this was something that always happened with second derivatives during implicit. You always had to plug back in your original derivative into your second derivative to get the full derivative in terms of that variable. So I'd have 1 over 25 multiplied by 1 over 25 times w minus 300. Honestly, remember, you don't have to simplify that much. You could leave it just like that, or if you wanted to clean it up, it was 1 over 625 times w minus 300. Okay, so you found the second derivative. Obviously, again, think of that in terms of concavity. You now need to use that to figure out, is this value that we found in that first part going to be an underestimate or an overestimate? Okay, so now remember that w of 0 is equal to 1400. So we're going to plug that into this second derivative. The second derivative comes out to be 1 over 625 times 1400 minus 300. Honestly, again, if you didn't have a calculator, it doesn't even matter what the actual value is. It matters that in this case, you're getting a positive divided by a positive, so this comes out to be greater than 0. This is telling you that this is concave up. So if you think about what a concave up curve looks like, that's the one that kind of looks like a U. Whether or not I have a decreasing or an increasing function, my line tangent is always going to be less than my curve. Therefore, since I found out that this is concave up, I can say the answer to part A is an underestimate. Okay, hopefully that makes sense. Again, just going based off concavity. So obviously if it was concave down, then my line tangent will always be above, and then it would be an overestimate. Okay, to do the remaining parts of this goes back to just regular differential equation stuff. So I'll let you take a look at the solution on our Google Classroom page. I just want to make sure I went over at least the first two parts of this because I know that those are a little different from stuff that you've seen before.